So today we're going to cover file I/O, which is actually pretty easy and straightforward because most of the tools that you are going to use to do file I/O you're already familiar with. For example, printf. But before we start, what is a file? Well, the idea when I say a file, the idea that comes to your mind is probably like a text file or your source file or something like that, where it's actually a unit of memory stored on disk. And that's not always the case, right? In fact, in a Unix-based system, everything is a file. A directory that holds files, that's a file. Directories are files themselves. Programs are files. When it's actually running in memory, that's a file. Buffers and sockets are also files. What's a socket? When one computer wants to talk to another computer, it opens over a network, right? It opens up a socket. And for one computer to send information to the other computer, they write to that socket. That socket is a file. So file output from one end, and on the other end, how does it read that data that's being sent from the other computer? It reads from that socket. So it file input on the other end, and that's how networking over TCP/IP works. That you're opening up a socket and you're reading or writing to that socket. Again, that's input and output. So when we say that we read from a file, that's a file input. When we say that we write to a file, that's file output. Now, files can be binary, which is just pure data, or they can be plain text files. We'll be mostly concerned with plain text files, right? If you're going to use binary data, like say images, like you've done before, or audio or video or something like that, bring in a library to do it. Because that's a lot of low-level kind of stuff. That's a lot of heavy lifting. So if you're going to be doing binary files, then that's when you want to bring in a library, unless you have to write the library, in which case then you will have to deal with binary data. Even plain text files can be structured data. For example, CSV files, we've looked at those, XML or JSON, or even base64 encoding. So what does a base64 encoding look like? Well, here, I'll go ahead and take some regular old data over here, some album data or something. And a base64 encoding looks like this, right? This gobbledygook down here. Definitely not intended for human consumption. What it's done is it's taken that data and it hasn't compressed it, it's encoded it using 64 characters. Lowercase a through z, uppercase a through z, 0 through 9. That gives me 62, and then there are two additional characters. I forget what they are, probably like an underscore or something like that. But basically, it's a way of taking binary data and encoding it in ASCII text, readable ASCII text, so that you can send it over protocols that don't support binary data. For example, one of those protocols is SMTP, Simple Mail Transfer Protocol. Anytime that you send an email to somebody and you've attached something like an image, that image is not sent in binary. Instead, it's encoded in some way, maybe base64 encoding, or usually it's a UU encode, which is an older scheme. And if you look at the raw email that you receive without it, not through an email client or anything like that, you will see something that looks like this. It's the binary data that has been transferred or has been translated, encoded using plain text characters like this, right? It's not intended for human consumption, but at the other end, you decode it, and then you can display your image in a nice, email client of some sort. But SMTP does not support binary data transfer, so attachments like this are you need some sort of encoding like this, right? So you can have pure binary data, or you can have something in between, right? CSV files, XML files, JSON files, or base64 encodings, right? It all goes back to EDI, electronic data interchange formats, where you're trying to transfer data from one computer to another computer, and they don't necessarily speak the same language. You need an interchange, you need a common language between them, and that's where EDI comes in. What we're going to do is we're going to pretty much stick with plain text encoding. Sometimes we'll look at binary encoding, but again, you're going to bring in a library to do that, right? Okay. Hello. Online, just online comments there. So the three basic steps for doing file input output are: one, you've got to open up the file, right? Two, you process the file. Now, if you're going to read the file or write the file, then those are two different operations. Once you're done with it, just like memory, you need to clean it up. You need to make sure that you close the file, because failure to close the file could result in undefined behavior. 99 times out of 100, the operating system will save you from yourself, but it's that 1% of the time that it won't save you from yourself, and you'll have file corruption, or the file won't be saved, or you'll be missing data, or something like that. All right, so let's go ahead and start with that first step right there, opening a file. It's really straightforward. In C, a file is represented by a pointer, right? Pointer. A special type that's defined in the standard input-output library called file star, right? It is all uppercase F-I-L-E, and it is a star because it is a pointer. Sometimes this is called a handle, right? Because it's handling the file. Now, when you open up a file, it makes sense that it's a pointer, because what it's happening is when you open up the file, it points to the first character in the first line. As you read either by line by line by line, or character by character by character, we'll do both today, that pointer will advance through the file. So if you start on line 1 and you read the entire line, that pointer, that file star, will be advanced to the next line. You read the second line, it automatically advances to the third, etc. Right? It automatically advances through the file as you read it, right? Or write to it, right? To open a file, use open, right? Which is just stands for file open, right? It takes two arguments. Those arguments are a string representing the path/file name to be opened, right? And representing, right? A string representing the mode. So for reading, for file input, you'll use an R, reading. This is file input. And for writing, you'll use, guess it, what it is? W, exactly, right? And this is writing, this is file output, right? Now there are other modes. For example, there's read-write mode, there's append mode, and there are a couple of combinations thereof. I'm going to keep it simple, and I'm just going to look at these two, okay? It returns a file star pointer upon success, right? So you open up a file and you start reading it. It's pointing at the first line, the first character in the first line. What happens if it doesn't succeed? If it does not succeed, it returns the only thing that it can. It returns null. Exactly, right? So why would a file opening not succeed? File doesn't exist, right? You want to open up a file for reading and it doesn't exist, it can't open it up for you, right? What else could go wrong? It's corrupted. It'll still open up in some cases, but then you start reading it and you get unexpected results, right? When can't I open up a file? Here's a file. I should not be opening that up for some reason. Because? Permissions, exactly. Should I be able to open up a system-wide password file, for example? Right? Probably not. So this can happen for any variety of reasons. It may not exist, right? Our program may not have permission, etc. Right? It could fail for any number of reasons. You can check for that by checking null. So let's come over here and let's go ahead and try it out on a couple of different files here. So for example, file star f is equal to fopen. Let me go ahead and open up a file called myfile.txt. It's just a text file, and I'll open it up for reading. Right? So now over here on the left, do you see any file named myfile.txt in the current working directory? Nope. So this is likely to fail. We can check for that by checking for null. If f is equal to null, right, then printf unable to open file. Right, there we go. Else, printf opened successfully. There we go. And when we compile and run this, of course, there's no file called myfile.txt. When I run this, of course, it's not able to open up that file. What do you think happens if instead of opening it up for reading, I open it up for writing? Yeah. Well, it doesn't have to exist, right? You're going to create this file and you're going to start writing to it, so open successfully. Now, on the left-hand side, do you see that the file was actually created? No, but that's for a different reason. Remember, every so often you have to kick it in the butt, right? And refresh it. There it is, myfile.txt. Now, did I actually write anything to this file? No. So if I open it up, there's nothing there. So blah, 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 blah. Here, I'll just mash the keyboard a couple of times here, right? There, save it. Right? And let's go ahead and end that. And one thing that I forgot to do here was to close it. We'll talk about that more formally here in a second, but just guess. If you use fopen or fopen to open up a file, what do you use to close a file? For close, exactly, fclose. Right? And then you provide it the pointer that you want to close, and it'll successfully close it. Let me go ahead and run this. And let me ask you, remember what was in that file? I mashed the keyboard a whole bunch of times. Let me go ahead and, in fact, let me go ahead and keep that open. And let me go ahead and run this program again, where I open that file for reading, or for writing. All right, it'll open up successfully. All right, I close it. Did I actually write anything to that file? Nope. So what happens to the contents of that file? Watch really closely. Gone. All right, lost and gone forever. There is no undo. There is no undelete. There is no recycle bin or trash bin that you can pull things out of. There is zero way of recovering from this. Right? It is very unforgiving. If you wipe out data with a program, that's it. Right? That data is gone. Period. Right? So, for example, what if I opened up the file that I'm working on right now? I'll copy it just for backup here. What if I open that up for writing? I didn't do anything, and then I close it. Well, it's still there, right? Until oh, oops. All right. So everything that I just wrote is now completely gone. Good thing that I backed it up, right, by copying it to the clipboard. Make sure that you are doing regular backups, right? Make sure that you are using GitHub or Git fully to, with your private repo where you're checking stuff in to the cloud every so often, right? Make sure that you've got backups, okay? And don't do things like this, where you're opening up your own source file, myfile.txt. Right? Remember, it's gone now. So, closing a file, right? Closing a file. All you have to do, you simply use fclose and pass the file pointer into it. Failure to correctly close a file may result in lost data, right? Corrupted data, or undefined behavior. Anything could go wrong, and if anything can go wrong, probably something will go wrong, right? Murphy's Law. Okay. Let's see. You can also open up a file using relative file paths. For example, let me come over here and open up the Etsy password file. Right? I think we've briefly looked at this before, right? If not, let's take a look at it. Should I be able to read the password file? Well, generally no, but there aren't any passwords actually stored in this file. You see these X's over here? They've been redacted. Instead, they're in the Etsy shadow file. More Etsy shadow. There we go. Which I'm not allowed to look at, right? Because of course there is sensitive information in there. So I can read one of those files. I can't read or write one of the other files. So if I tried to open up the Etsy password file for reading, it'll probably be successful. Right? A.out. There we go. Open successfully. But if I open it up for writing, right, it will not be successful because you should not be able to change a system level file like that with just your simple computer here, right? And oh, by the way, segmentation fault. Why? You tried to close a null pointer, so it failed. Unable to open file. Maybe we want to exit at that point because there's really no recovering from it, right? If you can't open the file, you can't process it, and if you can't process it, there's no point in you existing as a program, right? What about reading that Etsy shadow file? Right? Am I going to be able to do that? Nope. Unable to open that file. Okay. So these are absolute file paths. I want to start at the root file system. Under that is a directory called etc. We call it etc. In whenever you're in a Unix, you would usually pronounce this etc. Right? But in a Unix world, we call this etc. Right? Don't ask me why. And then under that, you have this file called shadow. You can open up other relative paths. For example, go up one directory, go up to another directory, two directories, and then go down into another directory, foo.txt, foo, and then in that bar.txt. So this is an entire path / file name. If you're just going to go with the current working directory, that's good enough. And that's going to assume that the bar.txt file is in the current working directory, right, wherever the program is being run. So you have relative file paths, you have absolute file paths, and you have current working directory file paths, right? Things that look like this. Right? I'm not sure why it's not text highlighting that. There you go. Absolute paths, etc password, relative paths where you go up one directory and then down another. Right? I'll leave that out there. All right. So now we know these two steps, right? We can open up a file, we can close a file. Now we need to talk about how to process the file, the actual meat and potatoes of this thing, right? So the first one is going to be the easy one, file output. And I'm saying that it's easy because you already know how to do it, right? You can use fprintf just like you would printf to print in quotations here, to a file. In other words, do file output, okay? There are lots of other ways, by the way, but I'm keeping it simple, and I'm showing you this one because it's straightforward and you know all about it already. So let's come back over here, and let's open up that myfile.txt for writing, because that's output, right? I won't bother looking and seeing if it is successful or not, and then I'll close it, right? So let's actually go ahead and print something out to that file. fprintf, right? Well, actually, if I just do printf, right, hello world, end the line, that would print out to the standard output, right? I don't want to do that. I want to print to a file. So fprintf. The difference here is that you provide it with the file that you want to write to as the first argument. All right? Let's go ahead and run this. And we'll see over here that in my file, now I have hello world. Okay? Let's continue. How do I print variable values? Well, if I've got a variable called x, and it's a value 42, I've got a floating point number, double y is equal to whatever, right? And I've got another, say, string, char name equals University of Nebraska, Omaha. Right, there we go. How would I print those to a file? fprintf, f, right? And then you would just format them. %d is equal, or x is equal to %d, y is equal to %f. Say end the line, x and y. Right? fprintf to the file f. Welcome to %s, where that's going to be the University of Nebraska, Omaha, and name. There we go. All right. Let's go ahead and compile that and see what the contents of the file are after that. Right? Again, there's nothing being printed to the standard output here now because I'm not using printf. I'm using fprintf to print to this file over here. Right? How many lines are in that file? Good question. Well, how many line numbers is it showing over in my editor? 4. How many end-line characters did I print? Do you remember? 1, 2, 3. Right? Is there an end-line character on this last line? No, you got to be careful. What if I had printed it like this instead? In other words, over here, I didn't put an end-line character in the last line. Right? It would look something like this. Now, how many lines are there? 3. How many end-line characters are there? Just 2. The one on the first line, the one on the second line. There is no one on the last line. So you've got to be careful there, right? Are there end-line characters at the end of every line? Not really. How many lines are there now? 8. 7 end-line characters, but the last one, the last 5 lines are all blanks, right? They're all empty, okay? So that might come into play later on. Remember that. Okay. Let's see. I'll save it like this. How many characters are in this file? How could I find that out? A couple of different ways. Right? First of all, I could have a long listing of all the files in the current directory here. And this column right here tells you how many bytes the file is. For example, these directories here are 4 kilobytes, 4,096 bytes. This file that I created was 75 bytes. 1 byte is equal to 1 character. So how many characters are in that file? 75. Or I could take it over here and put it into an online character counter, right? 75 characters. Even though it's not printing out the end-line characters here, it is telling me that there are, what? Spaces, words, letters. I'm not seeing any end-line counters here.
Paragraphs.
Oh, where is it? Paragraphs there. Thank you. 3, right? And it's interpreting those as end-line characters, right? Here's another way that you could do it. There is a utility called WC, which stands for word count. You can run it on any file, and you'll get that this is, I think that this is what WC. Print new line, word, and byte counts. There we go. So how many new line characters are there? 1, 2. That's what this column is. How many words are there? Words are interpreted as sequences of characters separated by white space. So that looks like there are 13 words and 75 characters total. Does that agree with over here? How many words? Yep, 13 words. It's probably just using the exact same WC utility of some sort. Right. Okay, good. Any questions on file output here? Because all you have to do is take everything that you know about printf, all of the formatting tricks, all of the placeholders, right? All of that knowledge, cut and paste, and know that you can use it with fprintf as long as you put the file first, the file handle first. Okay. We saw that again with sprintf. Do you remember that? Where you can print to a string. We covered that, right? Yes? No? Okay. Well, let's do it again then. All right. So instead of using fprintf, what I could do is I could have a string. So char full content. I'll just make it huge, 1,000 characters here, right? And I'll have sprintf into full content. Now I'm going to have to do this all in one shot. So there we go. And there we go. And then x, y, name. There we go. And print that out. I'm just going to print it out to the standard output here. Printf %s and full content. There we go. GCC. Oops, nope, that's wrong. Run it. There. Hello world, x is equal to 42, y is equal to blah, blah, blah. Welcome to the University of Nebraska, Omaha, right? How did that work? I printed it to a not to a file, not to the standard output, but to a string instead, using sprintf. Right? And I provided the string that I wanted to print to, the formatting that I wanted to use, followed by any variables that I wanted to print to the standard output, to that string. Right? So you've got now several printfs. You can print to the standard output, which, by the way, the standard output is a file. It's just a regular old file. You can print to a string. You can print to a file that's saved on disk somewhere. Right? All right. Okay. Now let's go to the hard part. It's really still not that hard, but file input. Let's go ahead and jump down here. Yep. All right. So I'm going to keep it simple. There are many ways of doing file input. Most of them are dangerous. A lot of them are complicated, overly complicated. We're going to keep it simple. We're going to use fgetC to read character by character. We're going to use fgetS to read line by line. Right? So understand what those names mean. F get C, file get, what do you think the C stands for? Character, right? You're reading a character by character, so you're getting one character at a time. F get S, what are you doing? Well, you're getting an entire line, up to an entire line, but what is a line? It's a sequence of characters. What is a sequence of characters? We call that a string. So F file get string, okay? So let's go ahead and look at the first one first, right? Reading character by character, okay? So fget C reads and returns a single character from the file, right? Let's come over here and set ourselves up. So that same file that I output, that my file.txt, let me go ahead and add a bunch of other stuff to it. Hello world, how are you? I'm fine, thanks. There we go. Period. Okay. Let's open up that file for reading. So file star f is equal to, now if you've got to open up multiple files, one for reading, one for writing, you can give them better names like input file, output file, right? I've only got one file here, so I'm just going to call it F. Right? Sometimes in a lot of tutorials you'll see H. Why? Because, well, FGH, that's close, but also H is short for the handle, file handle. Okay? So I'm going to go ahead and go with F here. Open. Oops. Spell it right. My file.txt for reading. Okay? Now let's go ahead and read one character. So I'm going to declare a character in order to hold it, and then I'm going to call fgetC on F. Right? That's going to give me a character. Let's print that out. Printf, read %C and the line, and I'll read in C. Let's do it for the second character, the third character, the fourth character, the fifth character. Right? So let's read 5 characters from this file, and then what should we do at the end? If we're done with it, close it. Right? Okay. So what is this going to output? Well, what are the first 5 characters of this file? Right? It looks like HELLO to me. Hello. Okay. There we go. HELLO. It reads one character at a time, automatically advancing to the next character for you. So that when next time you call fgetC, it reads in the next character, the next character, the next character. Now, should I be cutting and pasting like this over and over and over again? Probably not. Do I know how many characters are in that file? Well, if I use an online character counter, sure. If I use WC, sure. But what about in the context of this program? If I open up a file, do I know in advance how many characters I'm going to read? Probably not. So what kind of loop control structure should we use here? A for loop or a while loop? A while. While you are not at the end of the file, right? Then I will read a character and print a character. There we go. And get rid of all that. Okay? Now, obviously, that's not real C. How do I know if I'm at the end of the file? Okay? It would be null if it were a pointer, right? Only pointers can be null. So char s is equal to null, right? That would work. But this is a character, a single character. There is a very special character built into the C library called the null. Actually, nope, it's not even that, unfortunately, because you can put null characters into a file. It's not a good idea, but you can do that. There's this other character that's not even in the ASCII text table. ASCII table. Where is it? There we go. So it's not to be found in this table at all. Instead, it's this very special character called, while C is not equal to EOF. What do you think? All caps, EOF. What do you think EOF stands for? End of file, exactly. Right? It is defined in the standard input-output library, and if you take a look at it, its value is -1. Do you see a -1 in this table at all? Look real hard, but they start at 0 and they only go up from there, right? So that is not a valid ASCII text character. Instead, it's a special flag value to indicate there is no more characters in this file, right? You are at the end of the file, okay? fget.c returns the EOF character when you're done. Okay. Now let's go ahead and compile this and run it. It should read the entire file, but it's not going to be exactly correct. Let's understand why. All right, let's go all the way to the top. Okay, well, HELLO, right? X is equal to 42, comma, Y is equal to blah, 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 blah. And all the way down at the bottom, I get, I'm fine, thanks, period. And then a diamond question mark. What is that diamond question mark? That's the EOF character, right? Is it printable? No, because it's not even a valid character. So what ends up happening is that we've got corrupted data here, right? And it ends up printing this out, okay? So I need to rethink this while loop right here. What happens when we get to the end of the file? So we read this period, which is the last character in the file, right? We read that, we print it out, right? Then we come back up here because C is still that period character. We iterate one more time and get the last character, which is EOF. And then we end up printing it. Right? That's why we get this incorrect EOF value right here. Let's restructure this loop so that it's actually correct. What I want to do is I want to make at least one call before I start. Right? Because what if it's an empty file? That means that you're immediately at the end of the file, and this loop should not execute at all. Right? In fact, yeah, I'll show that to you here in a second. Right? What we'll do is we'll then print it out and then set ourselves up for the next loop by swapping these two values. Remember that you do have to be careful with the while loop because you have a lot more flexibility, and with more flexibility comes more responsibility. You have to make sure that you're not off by one, and we were off by one here by printing the end of file character. Okay, this should actually work now, right? And run it. All right, period is the last one that we read, and H is the first one that we read. Looks like we're correct. How can I be doubly sure that we're correct? Int count, right? Count the number of characters that you've read. So every time I read something, right, I go ahead and increment. Count plus plus. Remember, ls, la, right, that we have, now we have 120 characters in that file because I added a bunch of stuff, right? Let's go ahead and make sure that the online character counter agrees with that 120. I should get 120 at the end of this loop right here, right? So let's print that out and make sure. Printf, number of characters, %d, and the line, count. There we go. GCC, run this. And it should be 120. Oh, perfect, right? We've got at least 3 different tools agreeing with our program here. So I'm reasonably sure that this is correct. Hey, that seems kind of useful, right? It would seem kind of useful if we knew exactly how many characters are in a file, right? That's what this code is doing right here, right? With a little bit of extra. What if we were to put that into a function and reuse that function instead? Let's do it. Int count chars in file. Right? And then what we'll do is we'll have const char star file name. Right? And cut and paste my code here. Now, instead of always opening up myfile.txt, we'll take that as input. Right? Do some basic error handling. What if there is no such file? If file name, or if f is equal to null, right, I was not able to open up that file. So how many characters were in that file? Return 0, right? That's not an error code, right? It's returning the number of characters that it successfully read. Right? And I successfully read 0 characters, so it is perfectly valid to return a 0 in this case. Right? All right. Otherwise, I will get the character. I've got my counter here. While I'm not at the end, don't print it because I'm just counting them up. And then close it at the end and return the count. Right? Now all I have to do is call this to verify. Right? Count characters in file of myfile.txt, right? Int count is equal to, and we should get 120 still, right? We didn't break anything. Again, if something seems useful, like you want to use it at least more than once, put it into a function, right? And then reuse that function. Okay? All right. So fgetC reads a single character from the file. It returns a special EOF character. This is not a valid ASCII text character that indicates the end of the file. Right? So you can put it into a while loop and read character, 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 character. You can rewind, right? So in fact, there's a function called rewind. I'm not even going to show it to you because I'll let you look it up if you really want to use it. But every time you read a character, it advances that pointer. Sometimes you may want to go back, right? Why do we call it rewind? What do you think? So with modern music, of course, you can fast forward and rewind, right? But think back to what that meant, say, in the 80s. What did it mean to fast forward or rewind? The tape, right? It was on audio tape, and it was on a spool. And so fast forward meant that you forwarded the tape, right? And that's exactly what it means in this context too. Because how was data stored in the 70s, 80s, right? Not on hard drives, massive amounts of data, right? It was not stored on hard drives. They were stored on magnetic tape. In fact, to this day, magnetic tape still, as a cost per gigabyte of storage, is still the cheapest way of doing things, right? By far, right? Because solid state drives, expensive, hard drives, expensive, and in fact, tape backups are even more reliable as long as you don't get them near any magnets or anything like that, right? I think that they have a longer shelf life too. Not compared to optical drives like a CD or something like that. I'm not sure. I'm not sure who wins that battle. Somebody can look that up and let us know, right? Which one is better has longer term storage, optical drives or magnetic tape drives, right? But anyway, so that's character counting, right? You know what? I don't think I copy pasted it, so I'll just go ahead and put this version into the notes for you. All right. Let's see. There we go. All right. So another way of doing this is reading line by line. Right? So you can use fget_s to get up to an entire line of the input file. Right? But the input of the number of characters is limited to prevent buffer overflows. Right? So what do I mean by that? Well, let's just go ahead and take a look at the signature of this function. I'm going to cut and paste that. Right? The signature of the function is as follows. Right? It takes 3 arguments. It takes the string that you want to read it into, the size that you want to read, the maximum size that you want to read, and then, of course, the file that you want to read from. Right? So the first argument is the string you want to read the line into. Right? The second argument is a limit. Right? It will read at most size -1 bytes from the file and place it into S. Right? Stopping when the limit is reached or it sees an endline character. And don't confuse the endline character with the null terminating character. The endline character is /n, the thing that you've been using since day one. Right? So now the reason that it does this is because you don't want, if I've got a string that's of size 100, can I put a line that has 200 characters into that string? Nope, that would be an overflow, a buffer overflow, a memory overflow, right? You're not able to do that, and so it builds into this function a limit. This is going to read at most 100 characters or something like that. Why is it -1? Well, 0 indexing, yes, but what does it need to put at the end of every string to make it sure that it is valid? Null terminating character, right? It is -1 because it needs room for the null null terminating character. Remember, the null terminating character is /n, \n, not \n. Or it is \0, not \n, right? There we go. It's the null terminating character and automatically takes care of it for you. Excellent. Right? It's one of those few instances in which C will do our work for us. Cool. All right, the last argument is the file you are reading from. Okay? So let's just take a look at an example over here. Okay? Let's get rid of all this. And let's go ahead and open up that same file. F is equal to fopen myfile.txt. All right. And I'll open it up for reading. Right. Make sure to always close it. One trick that I always do is immediately when you write fopen, I immediately write the code to close it, and then I come back in and fill in the second step. So step 1, don't forget step 3 by immediately doing it since it's so simple, and then go back and fill in step 2. Just like if I've got memory that I allocate, and I know that it needs to be cleaned up, freed, I immediately write that code and then go back and start doing something else, right? Or start filling in the blanks. All right, so let's go ahead and read in one line. I'll need a buffer, char buffer 1000. Right? Now, I've just made this large enough to hold any line for this particular file. What if I gave you a file that had a line with 2,000 characters in it, right? Then it won't fit into this buffer. Right? So we'll need to look for a better solution more generally. But for now, 1,000 is enough to take care of this file, right? The longest line is over here, and certainly there's no more than 100 characters in it. Right? That's where I'm going to read it into. Right? So let's go ahead and use fgetS. We read into buffer at most 1,000 minus 1 characters or bytes, and we're reading from my input file right there. Okay. Let's go ahead and print it out. Printf line is equal to %s and the line, right? And buffer. Right. Let's go ahead and read the first line, the second line, third line, the fourth line. How many lines are there? Okay, good enough. All right, let's run this. There we go. There's the first line, hello world. The second line was x is equal to 42, blah, blah, blah. The third line was welcome. And then the fourth line was, well, blank, right? So it read the blank line. Except that this seems double spaced, right? Why is it double spaced? Why are there 2 end-line characters right here? Well, there's an end-line character in the file. And when I printed it out, what did I do? I added my own end-line character. So, observation. Observation. The end-line character, /n, like this. Start over. N, there we go. Is retained in the buffer if 1 is read. Right? So, if you don't want that in your input, you need to take care of it. Right? How could I remove? So let's get rid of all this. Right? How could I remove that last end-line character at the end of the buffer? No ideas at all? Okay. If hold on to the if statement here. I just want to get rid of it. Period. Right? So if I had hello world end line, how do I get rid of that last character? Like that. I could change it into the null terminating character. Right? Everybody should have done something like this. Right? Remove char. Right? That was due last night at least. Right? Remove char, the end line character. Right? You know how to do this because you've done it at least once. You removed all of those characters though. I just want to remove the one at the very end. So what is going to be the index of this string at the very end? Is it going to be strlen of buffer? HELLO. Is that the last index? 5 things. 0, 1, 2, 3, 4. So, -1. The last index is going to end up being something like this. So let's go ahead and chomp out the last character by saying buffer sub that last index is equal to the null terminating character, effectively eliminating what that character originally was. Okay? We call this chomping. I think it's from Perl. Chomp is just an operation where you remove the last or trailing white space and stuff like that. Right? Let's try that. Okay. There we go. Now, when I print out the endline character over here, the original endline character in the file is now gone. Okay. So you can, once you've read the point that I'm trying to make here is that once you've read it in from a file, it's just a string. Process it like a string. Everything that you've done with strings up to this point, you can cut and paste that knowledge now. Right? All you need to do is load it up from the file, and once you've got it in memory as a string, do whatever you need to do with it. Okay? All right. Let's try that over and over and over again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many were there? That's way more than there are, right? Am I going to be able to read 10 lines from that file that only has 7? Nope. So I wonder what happens. Oh. Ooh. There we go. So there's the last line where I chomp out the endline character. Right? Actually, I'm chomping out more than that, am I? Is there an endline character on this last line? No. What did I end up chomping out? That period. Now let's go back to your idea. Maybe I want to be a little bit more judicious about this. Let me go ahead and get rid of all of this. Undo, undo, undo. There we go. Right? Chomp out the last character if it is an endline character. Right? So now put in an if statement. If that last character is an endline character, then get rid of it. If it's anything else, like a period, leave it in. Okay? Now I'll go ahead and cut and paste this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Again, am I going to be able to do this? Well, yeah, but it's weird. I'm fine, thanks. Dun, 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 dun. Right? Right? I recompiled this, didn't I? Oh, God. I can't believe that. You know how I could have told that? If I followed my own advice and had the wall flag, right? Suggest parentheses around this statement. That's an assignment operator, not an equals equals. Right? So let's go ahead and change that. Sorry about that. Now I've got to cut and paste this all again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Oops. GCC. No warnings this time. A dot out. There. I'm fine, thanks. I'm fine, thanks. I'm fine, thanks. I'm fine, thanks. All right. When it gets to the end of the file, what happens here? Yeah, the buffer doesn't change, right? So how do we know when we're at the end of the file? Right? Take a look at the return value there. What's the return value? A char star. Right? So the return value tells you when you're done. The function returns a pointer. Usually, this points to the buffer, right? To indicate that you successfully read a line from the file. Right? Otherwise, when it gets to the end of a file, it returns null, and the buffer is unchanged. Right? So now we can use that to determine if we're at the end of the file here. Don't copy paste, copy paste, copy paste, however many times, because you don't know how many lines are in there to begin with. Right? So what I'm going to do is I'm going to capture this value in a pointer. Right? And while that pointer is not null, while the line is not null, I will go ahead and chomp it out, print it out, and then set myself up for the next iteration by calling forgets again capturing that return value. Now let's go ahead and get rid of that. Come on. Too close. There we go. Let's go ahead and run that again. And now it will only read each line of the file exactly once. And it'll stop. Right? There we go. If you change the file, right? Good to know. How is your friend? Right? Whatever. Right? Put in a bunch of other additional lines here. I don't even need to recompile, right? Because it's opening the same file and the file has changed. Right? So the program's not changed. All I've done is program it to read the entire file line by line until you get to the end. Okay? And by the way, could you use this? Could you adapt this so that you could count the number of lines? Yeah, all you have to do is put a counter into this while loop. Okay? Otherwise, I'll go ahead and put this into the notes, and then we'll try to break it. Oops. All right. So how are we going to break this? Remember that it only reads at most 1,000 characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0. There's 10 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 100 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 1,000 characters, and there's over 1,000 characters on the first line. Let's see if this still works. It does, but what does it do? Here's the first line, and it reads at most 999 characters. Again, why 999? Why not 1,000? The null, well, at the end we need a null terminating character, right? And so consequently, the next time I call it, it's still reading that same line, right? It's just going to read whatever is in the rest of the line. Now, this is important if you're actually processing data, right? That if you're processing, say, DNA strings that are millions of different characters, right? Typically, what they do is they put it into a standard format so that they don't have really long lines here. Because do I have a file? I don't think I have a utility here, unfortunately. Otherwise, usually if there's this utility called file, it'll say it's a text file with really long lines. Right? It'll actually say that. Right? And this has a really, really long line. Usually what happens in data like that is they break it up so that there are no more than, say, 72 characters per line. Right? But if you do have data that ends up with being a really, really, really long, like this, right? Million digits of pi, right? There's a website, yeah, 1 million digits of pi, right? If you've got very, very long pieces of data like this, right, with no end-line characters whatsoever, then you do have to be careful about that. In fact, if I've cut and pasted this into my file, it's infinite scrolling, so it'll just load up more here. I'll only go that far. Right. Let's put that into my file. There we go. Yep, it's only one line. All the way back at the beginning. I know how to get there. There we go. I've jumped out back to the beginning. Let's go ahead and run this and see what happens. Right. There we go. Right. It read it, but it only read one line. It just had to break up that line every 999 characters. You can come back and you can say, well, okay, 10,000, 100,000, 1 million. Can you go to 10 million? No. That's 10 megabytes. Can you fit 10 megabytes on your program stack? No. Therefore, if you want to process a file that has 10 megabytes of lines and not break it up, what do you need to do? Allocate it using a pointer. Right? So, keep that in mind. Right? I think that if we give you a problem like this, we would give you a hint and say that you can assume that there are no lines more than 1,000 characters or 10,000 characters long or something like that. Right? We would put a reasonable restriction on this because, of course, you would have to have a more sophisticated solution than what we presented here to handle all that stuff. Okay. All right. Any questions so far? All right. I was not able to break it, but let's break it in a different way. All right. So, like I said, we're going to focus on plain text files, but let's think about binary files at least for a second here. because you're going to run this experiment in your labs today. Binary files, right? So consider a large integer value, say 2.147 billion. 123, 123. There we go. So my question here is, if it is stored in plain text, how many bytes does it take to represent? If, in fact, if 10 of them, if 10 copies are stored, let's go like that. Right? If stored in binary, how many bytes? Right? If it is, let's keep it simple for now. All right, 2.147 billion. That's small enough to be represented by an integer, right? Let me go ahead and take that and put it over here. Int x is equal to. There we go. Now, if I were to put that in that file over here, let's get rid of pi, right, and put it over here. Let me go ahead and save that, and let me go ahead and use one of my tools, like say word count, to determine, or LSLA, my file, to determine how many bytes that took. Do you see that number right there? How many bytes is that? 10. Why? This is not the number 2. This is the character 2, which has an ASCII text value of 50 right here. This is not the number 1. This is the character 1, the character 4, the character 7, and then 6 zeros after it. How many characters are there right there? 10, right? 10 bytes, so 10 characters, 10 bytes. The answer is 10. Right? If it's stored in binary, how many bytes is it? Remember, it's just the size of int. This is typically what? 4. All right, 4 bytes versus 10 bytes, who cares? Up this to big data. Millions and billions and trillions of integer values, right? Now is 4 versus 10 a lot different? Yeah, 2.5 times as big. Now you're talking about storing something in binary. You're only talking maybe a couple of gigabytes versus a couple of terabytes instead. 2.5 times as big, right? Or not magnitude scales, but you get the idea, right? So let me show you what you can do to store things in binary instead. What I want to do is I want several copies of this to show you how egregious it can be. So int values, right? And I'll go ahead and say that value in 1, that value in 2, that value in 3, that value in 4. That's 1, 2, 3, 4, 5 things. 6, 7, 8, and 10. There we go. Right. So remember that that's going to be 10 values right there. Okay. Now, if I were to output this to the standard to a file using regular old plain text, right? Let's do that because we now know how to do that. Fopen numbers, right? .txt, right? And we'll open it up for writing. Right? And then I'll iterate through that for int I equals 0, I is less than 10, I plus plus. Right? Fprintf into the file %d and the line and number values of I. There we go. What did I forget to do? What is the third step that I should do? But close it. Right? There we go. GCC. Let's run this. Refresh over here, and you'll see. Come on. There, numbers.txt. There are those There are those 10 numbers. Now, if I did an LSLA of that file, numbers.txt, right? 110 bytes, right? Why? Because each one is 10 bytes plus an endline character, so 11 bytes. There are 10 of them, so 11 times 10 is 110 bytes. Right? Let's do the same thing, but in binary instead. Right? So what I'm going to do is file h is equal to fopen numbers.dat. Dat would be short for data. File extensions don't really matter in Unix. That's a Windows thing. Right? Some of you have experienced when you download a makefile And Windows is insistent that it puts a .txt extension on it because it thinks it's a text file when it's not. It's a make file, right? So that's when you have to, change the Windows setting because you're not just a regular old consumer that's using Windows, grandma using Windows to look at her Facebook photos or something like that. You are now a developer, and you need to see things like file extensions, right? And you need to tell Windows to knock it the hell off, right? That's something that's been in Windows since day one. It's actually inherited from DOS, where file extensions actually mattered. But anyway, let's go ahead and open that up for writing, right? Now, I'm not going to write those things as plain old text values, right? What I'm going to write them as is binary, right? And for that, I need to remind myself, I think it's for write and for write, right? There we go. So, for read and for write, those are like fprintf and fgetS or fgetc, except that it's for binary streams, okay? The way that it works is you provide it the pointer to the thing that you want to dump. So let me go ahead and go write this, fwrite, right? The pointer to the thing that I want to dump to the file is values, right? The array. Then you need to specify the size of it. How many bytes are in each? Well, that's size of int. And then how many are in that array? Well, there are 10 things in that array. And then finally, the stream that you want to dump it to, in this case, h. Right? And then you can close it. H. Right? I didn't have to go into a loop because all of that information was placed right here. Write 4 times 10 bytes from this value right here into this file right here. Right? So predict, how many bytes is it going to write? 10 integers, 4 bytes each? I agree, 40. GCC. Run this. All right, there we go. Refresh over here, and you see, come on. Oh, .txt, duh. There we go, .dat. Sorry, we overwrote our other file. I want both of them there. All right, refresh this. Both of them are there. There's numbers.txt, like it was before. But now if I open up numbers.dat, do you think I'm going to be able to read it at all? Nope. It's just a bunch of binary, right? There it is, right? But if I list out how big it is, LSLA, numbers, everything, right? One of them is 110 bytes. That's the plain text file. One of them is 40 bytes, just like you predicted, right? Now, how would I read that in? Well, man, for read, right? There's its companion, right? You will read into this pointer however many bytes each thing takes, however many of them there are from this file stream, exactly the same. And so you can write binary, you can read binary. If it's not intended for human consumption, right, then go ahead and stick with binary data because it is, in general, it is way more compact right here. Multiply this by 1,000,000, and now you see the huge difference. 40 megabytes instead of 110 megabytes, right? Not orders of magnitude, but 2.5 times as big, at least for integers. For doubles, now the difference is even greater, right? Okay. All right, yeah, go ahead. Well, because it's binary, right? It's trying to interpret it as ASCII text, and it can't, right? So if I go more numbers.dat, right, there it is again, in a different interpretation. If I do a hex dump of numbers.dat, right, a hex dump, hexadecimal dump, there's the first, let's see, that's going to be the first number. So hex to integer online. Online hex converter. Hopefully this will work. Oh, come on. All right, that's obviously spam. Rapid tables, hex number, convert. Nope, this is probably going to end up being Big Endian. You talked about Big Endian in your, I keep asking the digital logic design classes, right? Still has not taken them? All right, this might be Big Endian. So 0CE9, let me reverse these. And this would be 8FF7. There we go. Convert this. Nope. All right. So decimal to hex. Let's go backwards here. What were the values? Here's that value. There we go. Convert it. So that's what it should be. What would the hex dump say? The hex dump said, okay, so that's the second part. That's the first part. There we go. That matches. It is word big endian, so the words are swapped around here. Each one of these is what is it going to be? 4, 4, 4, 8. So four bits each on each one of these, right? 4 bits for 16. Yep. So there's the actual number that's listed right there, right? And that corresponds to this number right here. It's just ways of thinking about numbers in binary versus hexadecimal versus decimal, which you're used to thinking about, right? Okay, so why is it garbage? Well, because it's not intended for human consumption, right? It's intended for a computer. I think we could look at the binary too, right? Yep, I mean, sometimes it doesn't even let you open it. DAT is usually data, and it's usually binary of some sort. There's the binary, all right? It's just a bunch of zeros and ones. And it's attempting to take those zeros and ones and interpret it as ASCII text. It fails, and that's why you're getting this garbage right here, right? You're getting control sequences of some sort. Right, if you open up a PDF, right? Now, if you open it up in a PDF previewer, obviously, you'll be able to see it, right? But if you open it up in a plain text editor, right, it's going to have a bunch of binary crap that looks like this, right? Yeah, DAT file, whatever you want to call it, right? All right. So, any questions on that? Otherwise, you'll do that same experiment today in your labs and see what it looks like. No questions? Go ahead.
Big Indian?
Oh, no, big endian. Big endian, right? Like the end of it. Big endian meaning, here we go. Little endian and big endian refer to bytes that are most significant. So when you write out 1,225, right? You write 1, 2, 3, 5. Right? The most significant digit is over here because we read left to right. Right? A computer, sometimes it's more efficient to read right to left because of how the byte sequencing works. So little endian and big endian are reversals of those. So it'd be like writing 1,234 as 4321. Right? It would not make sense to us because we're humans, we're used to reading left to right. Right? Not all languages are like that, by the way. Some languages read right to left. And computers, in particular, in a lot of instances, also read left to right. And so you reverse them, and that's little endian. Right? All right. I'll see you in lab then, if there are no questions.